Hello, everyone. My name is Rolando Garcia, and I'm a PhD candidate at UC Berkeley. And right now, I will show you a demo that was presented at the EPIC retreat this year. So the first thing we're going to do working out of a Jupyter notebook is install FlorDB. I've taken a screenshot here that shows the project contents on PyP in case people have questions, they're able to browse and learn more. I don't need to install FlorDB on my machine because I've already done that, but you should be able to verify that Flor was installed properly and that you can import Flor. Additionally, we're going to train some models. So we have prepared an ML tutorial in the UCB EPIC repository. So I will clone that repository, and there is just a single main.py file that we're going to be working with. So I will switch directories into the directory that contains the ML tutorial repository. And the first thing we're going to do is instrument main.py for Flor record replay. What that means is passing in objects to checkpoint periodically to Flor.checkpoints, and then wrapping iterators for the main epoch and the nested training loop in Flor.loop. I have split the screen. We will continue to use the Jupyter notebook at the bottom, and we will be looking at the source code on the top. The first thing I want to do is import Flor, as well as import Flor's model training kit for efficient record replay. We see that there's some hyperparameters. We're working with the MNIST data loaders, and all of the usual boilerplate code that is typical of PyTorch programs. Down here by the main loop, I will start by selecting the objects that I want to checkpoint periodically. In this case, it's just model and optimizer. And I will also wrap the loop iterators for the main loop, as well as the iterator for the nested training loop. That's all I need to do for Flor to manage efficient record replay. Additionally, I will want to log some training data. The first thing I want to log is the loss. And I will also want to log the accuracy. Now, beyond just the classic metrics, it helps to look at the confusion matrix, where we see the kinds of errors that the model is committing in misclassification or misdetection, so that we can better assess how that model might behave in production. In order to log the confusion matrix, I will create a few local variables to manage the labels and the predictions. Here we want to copy the labels from GPU memory to CPU. And we also want to repeat the same steps for the predictions. This is how you would log a confusion matrix regardless of Flor. So here we want to log the confusion matrix, give the logging statement a name. And I have implemented a helper function, but it's just Seaborn logic, pandas, numpy, nothing too special. And so it's a matrix. We want to give the X and Y axis names. So we will get those labels now. It's MNIST, so the class labels are just the digits from 0 to 9. And that is everything I have to do for the first run. I scroll back down. And so what we will do next is write the log to Git and then write checkpoints to a shared drive. Additionally, because iterative ML is very high velocity and things change very quickly, we will want to commit changes to Git on every run. So the way that I do that is I call Python on this main script with the Flor argument and then a name for the run ID. In this case, it's Epic Demo. When I run this, Floor is going to fail as a safety precaution. That's because I'm currently working out of the main branch, as you can see. Instead, Floor would like me to work out of a Floor shadow branch, which just gives Floor permission to commit automatically. That way we don't pollute the user commits with automatically generated commit messages. So we're going to create a new branch, and we will switch into it to give Floor permission to commit, and then we're going to run Floor record. As the model starts to train, we can scroll back up and see that this is just a classic deep learning scenario on MNIST. We have two linear layers, a rectilinear unit with a hidden size that is determined up here with the hyperparameters, a hidden size of 500 neurons. The model is training. It's about halfway done. Down here, we see that the checkpoints are declared before the beginning of the main loop. And as the model trains periodically, Floor will decide when it's time to take that checkpoint automatically. We see that the training has completed with a really high accuracy because it's a simple problem, and Floor has written the log records locally. Next, we will read the log records that we just wrote by past runs into a pivoted data frame. We do that by importing log records and full pivot from Floor. As you can see, the values that we logged, the loss, the accuracy, and the confusion matrix are available in the pivoted view. And so we will display the logged confusion matrix. It will be just a single confusion matrix because it's what we've logged. The way that we read this is that the lighter values are higher. And so number 3s can look like number 8s to the model. Next, we're going to load log records from someone else's experimentation. First, we look at remote branches available in the ML tutorial repository. We see that there's Floor.shadow compressed. So this corresponds to an exploration that an undergraduate student performed to try to reduce the size of the model and reduce the prediction latency without hurting the accuracy too much. So we want to switch into that new branch. And we see that the code has changed above. And like before, we're going to read the log records written by past runs into the pivoted data frame. The first thing that strikes me is that there's a lot of missing data. And that's because my colleague and I are logging different things. My colleague did not log the confusion matrix or the accuracy, and we did not log the hidden size, the learning rate, or the batch size. If we look at the code, you can verify that in the evaluation section, we don't have the confusion matrix logging data. We will maintain this code view so that we can see how it changes as we proceed. We check that the confusion matrix, there's only a single confusion matrix for us to look at. It's the same one that we had seen before because it corresponds to the Epic Demo run, and that's from earlier today. Now, wouldn't it be nice if we could send our logging statements back in time so that we could better compare our models using the same evaluation logic and metrics? So in order to do this, we're going to call Floor replay. We will select the logging statements that we want to propagate back in time to other versions. And then we will condition on runs where the confusion matrix is null and where the hidden size is less than 250 neurons. So if we were to scroll back up, we would see that confusion matrix is null for all of these different versions, and the hidden size is less than 250 for about 3 of them. When we call Floor, it asks us if we want to continue running given the replay schedule for about 13.75 seconds. And we say, yes, we allow it to continue. What Floor is going to do is select the versions from the pivoted view that satisfy the where clause, estimate the time it will take to replay the selected versions, check out the versions one by one, patching the code to include additional logging statements included in the apply vars, and then replay the patched historical versions using memoization and parallelism as possible to retrieve log data. because Floor was calibrated on a different machine, the time estimate is a little bit off. But we can scroll back up, and we should expect to see values for these 3 rows to have been filled in now. So we recompute the pivoted view, and we confirm that that's the case. When we scroll back down and preview, we can see that we now have generated confusion matrices for the runs of my colleague. And so now it's possible for me to assess not just the accuracy of the model that was trained about a month ago, but also see whether the kinds of mistakes that it makes are compatible with my production distribution. It seems like this model, the increased LR, might be more generalizable. And it makes reasonable mistakes, like mistaking 9s for 4s. Okay, well, that's it for the demo. Thank you very much for your time. If you have any questions or comments, please do not hesitate to reach out. I have put my email at the bottom of the demonstration. Thank you so much, and have a great day.